So I'm here to present about impact of metrics on observability using eBPF. eBPF is a platform with a Linux kernel. I'm currently working with Kingston University as a mentor and an open source contributor with a drift detection framework called Evidently, a software called Evidently company, and also one API software innovator. So I've got 7 to 8 years of experience working with PHP, Python, Node.js, and SQL. 2 years experience working in machine learning and artificial intelligence projects. During one of the hackathons, I won the phase 1 of the Intel AdLink hackathon. I got this Busy AI kit, and I was also part of 3 course-based scholarships with Udacity. Thanks for the opportunity to speak to you. It's been a pleasure to introduce the topic to you. So let me discuss about what an eBPF is. eBPF is basically a Linux kernel platform where you can conduct observability, perform observability, or integrate observability into the environment. And it starts with a Clang C++ compiler with the LLVM backend, and it converts to BPF bytecode. That bytecode is called by BPF syscall, and the program is verified using a method, which is then later compiled by a JIT compiler to native instructions. So why should we use eBPF? eBPF allows you to integrate observability on every OSI stack, like the level 7 stacks that you have. Then a lot of tasks within the observability are compliant with licenses. We can create custom metrics. And one of the advantages, like it improves encapsulation of network packets, data, and functions. Then consider like you have AI tasks that require personal data processing. eBPF comes into place to assist in observability. eBPF mentions there are observability mentions there are 3 particular tasks, which is like logging, tracing, and metrics. And these are like recommended by EU GDPR rules. So for example, if you take face recognition in logging, EU GDPR rule states an identifier can be in the logs, but not an image. So that is quite key because you can integrate metrics and you can encapsulate data and move the stack up. So this is like basic structure of an eBPF Linux kernel. There will be a lot of programs attached to eBPF kernel, and they will be run by sharing a base code or base layer kind of a network, like a Docker system, for example. So it will be like apps and connected over the Linux kernel. So this is the verification program that I spoke about. So there is a user space where the program exists, and the program is sent to the verification process, and it is executed, which gives the output. So the advantages of program verification are it allows privileged process to be run inside eBPF. It won't damage or crash the system. It always runs to completion without endless loops. This is an application of eBPF used in SDN, software defined networking, where the layers are getting used within an eBPF platform. The Metronome systems does this. So we have high-level language, intermediate representation, primitives, and targets. This is an example where they actually have a glue network. So instead of going through the stack entirely, they have a Cilium glue network with eBPF integrated, and the apps are connected through that. So you don't have to have TCP like TCP network that those layers integrated, and because they'll be part of the glue network. Some of the C++ tools that I found from eBPF platform are Boost libraries, then OpenGL, and LR, Conan, which is a package manager. Oat++ is open source C++ web framework. Infer is a Facebook static analyzer toolkit. Then Java CPP is, you can run C++ inside Java, and Python, Maven, Clang compiler, etc. So how are the metrics integrated? Like, what are the metrics? Metrics do exist in a BPF map. So this is a BPF map, for example, and BPF maps from a user space to a kernel space. So this is where the program exists. It's on the next slide. And it performs tracing, logging, and monitoring inside the map. So this is the program is initiated first, then it calls, it executes this is called, eBPF is called, and the function is called here. There's an event getting called, and the data is getting passed here, and performance actually is measured. So in the program, actually, this is an example of kind of passing a command and a message. So the message would be like hello world, and there would be a command for that. And you actually, the metrics will output the size of the data and the message as the output. So why should why is this advantageous? Because I spoke about all the usage of level 7. Network layers, OSI layers. So there was one application based upon Netflix Vector. What they did is they used Node.js based application and some PCAP software using Python. Then they integrated, but it was a failure because they are not using all the Linux kernels, and this GitHub repository has been archived now. So yeah, this was not built within a. I also attended a hackathon. So this was based on citizen e-government services. So I also found out that for a citizen service or for a data scientist citizen service, you should have these observability. You should have an eBPF-like platform integrated rather than integrating for a business user, which Netflix Vector has done. And otherwise, there would be a lot of legal battles happening, which would violate policies and regulations. So this is an open telemetry BPF commit contribution. There's a lot of commits happening in a July-October period, and the community, the commits are growing. So my article was about regime detection and drift detection, and I want to talk about drift detection because this is where you can quantify a risk to the data process. Like, for example, you can consider software development lifecycle, hardware development lifecycle, and data lifecycle as separate. And you have these structures inside your eBPF platform itself. And the data can be data can be extracted from the eBPF platform, and that would enable us to understand more of logging, tracing, and tracing, for example. So my drift detection project was on phase aging. So I got about 94% accuracy with real drift detection technique using a classifier. So what I did was actually I produced a manifold of faces, and where actually these age eliminated faces was presented on the manifold, and these are the real images. So I extract features based on these distances, and finally arrived at 94% accuracy. So there was the shift in there was my finding was like shift in the face is observed to separate elder and younger faces separately, and integrating this drift detection inside an eBPF is feasible on Android cameras as well as servers. So I actually came up with a hypothesis. So this is from, let's say, for example, you have these face images manifold. So there's such a manifold exists for images as well. For any image, for example, object classification images where they exist alone, or possibly a scenery image. Then some of the images need to be privacy protected. So let's consider face images are privacy protected. So you can integrate the drift detection algorithm to understand whether they actually validate the faces correctly and put it inside the eBPF platform.